Yeah, okay. We want to talk about weed seed dormancy. Now, weed seed dormancy is like a resting stage, right? If we have crop seeds and put them into the soil after planting, we expect if there's enough moisture, we expect the crop seed to germinate and emerge. But with seed from the weeds, some will germinate and some may remain dormant. They may not germinate. Now, this failure to germinate is what we simply call dormancy. The germination will happen later after a resting stage. So what is dormancy? It is a state in which viable seeds, it could be spores or buds, which fail to germinate under favorable conditions, such as moisture, temperature, and oxygen. Everything is there, but the process will not take place, the process of germination. So dormancy is actually the failure of viable seed to germinate under favorable conditions for growth of the seedling. So here we've got seeds of Datura stramonia. Some may germinate, some may not. This is the germinating seed. When you see the radicle coming out of the seed and the plumule also coming out of the seed, then we have germination. These are the parts of the seed where we have the radicle which will actually protrude first. Then the plumule will also emerge. So what is the germination process? It is the resumption of embryo growth, and if you look at these seeds, inside there is the embryo. So the embryo is the resumption of embryo growth and the emergence of the seedling from the seed. Process of initiating growth in seeds, resumption of growth of seed of any vegetative part. This can be regarded as germination. The process requires oxygen, temperature, right temperature, and sometimes light is required. In the case of photoblastic seeds, we can have live seeds in the soil, but they may not germinate, and we refer to these seeds as dormant. So what are the types of dormancy? Actually, these were defined by Harper in 1975, who said that some seeds are born dormant, and that kind of dormancy is known as innate or primary dormancy. You have the seed which is already dormant, when it is produced, and that dormancy is innate or primary dormancy. But some seeds, when they are produced, they can germinate but they will acquire that dormancy. That is what is known as induced dormancy. But some seeds may have that dormancy forced upon them. It's known as enforced dormancy. So there is innate dormancy, there is induced dormancy, the one which is acquired, the one which is forced or enforced. That one is known as that is an enforced dormancy, the one which is forced or thrust upon seeds. So induced and enforced dormancy constitute what is known as secondary dormancy. Here I've got a schematic representation of the three types of dormancy. So at the top we start with what is called seed dormancy, which we can divide into two: secondary dormancy and the primary dormancy. Primary dormancy is inborn or innate dormancy. The seeds, when they are born, they are already dormant. But with this secondary dormancy, we have got two types: induced dormancy and enforced dormancy. I think let us stop here so that I will explain these three types of dormancy. So when we talk about wheat seeds, they can have three types of dormancy: inborn or innate, number one; number two, enforced dormancy; number three, induced dormancy. This is why the seeds can remain in the soil being viable for a long time. Now, let us focus on the types of dormancy. The seeds from a single wheat species may exhibit one or more types of dormancy, or all the three in succession over a period of time. This is for survival. We can use this example of a wheat seed, which can alternate, types of dormancy. Let us start from seed dispersal. Now, from seed dispersal, you can have a plant with innate dormancy. It's not going to germinate because of inherited dormancy from the mother plant. Now, after seed shed, let's suppose we are in winter under cold conditions. The seeds will undergo stratification, let's say around June, July, somewhere thereabouts, when we have low temperatures. This stratification will change the ratio of inhibitors or hormones and cause the seed to break its dormancy. So we follow that seed. After the land has been disturbed, then it can actually germinate in summer. And more seeds are produced, and they continue to follow this cycle. But in some cases, the seed can go into induced dormancy, and it will fail to germinate. So it will circle. There's no seed production here or germination because it's undergoing induced dormancy. But somehow it may end up in the outer circle and follow the normal process, or from here it may be temporarily go into enforced dormancy, which are caused by environmental conditions which may not be suitable. But when those conditions are removed, germination can occur and it joins the normal cycle. So to speak, what I am saying is that the wheat seed can change its dormancy status. Either it follows the normal cycle, where it can break its dormancy, form germination process, produce new plants, or it can undergo enforced dormancy temporarily, then later join the main cycle and produce plants. Or it can circulate under induced dormancy without producing any plants, but somehow it may come out of it and follow the outer cycle and produce plants. So these changes ensure that the wheat seeds don't just germinate, and it means survival for the wheat seeds. I think that is the message which we want. Now we are going to talk about the innate dormancy. This is the dormancy when the seed is produced by the mother plant, which is the wheat. And we are going to spend more time on the innate dormancy, because that is the dormancy which is prevalent within the wheat. Now, primary or innate dormancy is the dormancy which is inherited from the parents. It is genetically controlled, and the seeds will not germinate if exposed to the environment which is conducive to germination. So innate dormancy or primary dormancy, it's inherited from the parents and it's genetically controlled. And because it depends on the genes. Even if the conditions are favorable, there's no germination at all. So what does it involve? It could be through morphological or physiological factors which cause this type of dormancy. So we are going to look at the morphological characteristics of seeds as well as the physiological characteristics of seeds, which are genetically controlled. There are some seeds which, when they are shed, they possess immature embryos inside the seeds. And for those seeds to germinate, the immature embryos they have to grow and become mature so that the seed can germinate. We call this period an after ripening period, for the embryo to mature. The examples of such weeds could be Xanthium strumarium, which can produce seeds which are just dormant. It can also be Acanthospermum hispidum, which can also produce seeds which are not mature. They will become mature after seed shed. Now on Xanthium strumarium, you can have two types of seeds. We call it polymorphism, where they produce morphologically and physiologically distinct set of seeds which have different after ripening periods. It's in Xanthium strumarium or cucurbe. Yes, there is this after ripening period, but it varies among seeds, and we call it polymorphism in the Xanthium strumarium. But in the Acanthospermum hispidum, there's no variation at all. So this is the Xanthium strumarium, which can produce different types of seeds. In fact, if you crack that shell, you may have two seeds with different germination characteristics. This is for the survival of this weed. Now, after talking of after ripening period, there's also what is known as embryo dormancy. This is the failure of the mature embryo. This is actually a mature embryo which is supposed to germinate, but it will fail to germinate. Now, embryo dormancy is controlled by cotyledons, and if you want germination to take place, you may have to cut off the cotyledons. Then the germination process can occur. This is common in this plant known as Fraxinus species. But I don't have a good example for local weeds. Probably we may have to look for it. Now, embryo dormancy may also be controlled by a number of substances or hormones. Ethylene can stimulate the germination of several weed seeds. In Avena fatua, ethylene levels increase just before germination. So ethylene levels within seeds can regulate germination in Avena fatua. We talked about stratification or low temperatures or chilling. This chilling process can increase a hormone known as gibberellic acid. Once that hormone is increased, it can actually affect germination. Gibberellic acid stimulates degradation of food reserves in the endosperm or cotyledons, which is an important process in germination. So you want the high levels of gibberellic acid or gibberellins to cause a germination process. Abscisic acid is also important. Abscisic acid deficiency is associated with the absence of primary dormancy. So if you have a lot of it in the seed, it can cause dormancy. So ABA is synthesized in the embryo and endosperm. It is then the balance between gibberellic acid and the abscisic acid which can determine dormancy in weed seeds. If you want a lot of detail about seed dormancy, you can read this journal. So dormancy or germination process can be a lot of processes as indicated by that diagram. And there's no need to remember this, but probably to read that paper and understand how these things are linked. Here we are looking at embryo dormancy, which is non-hormonal. Other non-hormonal compounds like phenolics, unsaturated lactones, short-chain fatty acids, and coumarin. These are other substances which can inhibit the germination within certain species. So if you want germination to take place, you have to remove these substances through leaching and oxidative destruction of these chemicals. If it is oxidative destruction, it could be a natural process within the seed. Then it can cause a breaking of the dormants. Now the outside coat of the seed can also impose dormancy. We call it the tester. The seed dormancy in many species is imposed by structures which surround the seed. This could be the tester, pericarp, bloom, palea, and lemma in cereals. For example, in Avena fatua, the palea or lemma, it is responsible for coat-imposed dormancy. This is the coat. So this can prevent entry of gases or water. But if you can pierce the coat, you can induce germination. So this is the seed of Avena fatua. Avena fatua seed. We are not really interested in the parts or naming of these. But here we just want to show that it is the outer part which is very strong, which cannot allow gases or water to penetrate.